Advanced Algebra Function and Graphical Reasoning 3.3, a logarithm is the exponent necessary to make one number another. So if we're missing an exponent or desiring an exponent, then logarithms is the topic or the thing we're going to look for. So the first thing to understand a logarithm is to change from exponential form. Okay, switch to logarithmic form here. So this is an exponent or exponential form. A simple fact that by now we know 4 to the second power is equal to 16, but in logarithmic form it looks like this. So part of understanding it is to know the order and the script of how to write this. This is LOG is short for logarithm. This 4 is intended to be small and low, not a normal script. It's called a subscript. So 4, 16, and 2 are both written in normal script. We read this log base 4 of 16 is equal to 2. This is not to be confused with 4 to the 16th power. And what this means is exactly what you see in yellow. Log base 4 of 16, if we didn't know the 2, is asking for the exponent necessary to raise 4 by to make 16. Okay, so if you ignore the 2 for just a moment, when you see that 4 and you see that 16 in this configuration, you are looking for an exponent. More examples, switch to exponential form. So let's say we have this, log base 5 of the fraction 1 over 125 is equal to -3. So again, this is saying what exponent must I raise 5 by to make 1 over 125? And the answer is you must raise 5 to the negative third power to equal 1 over 125. Again, getting used to the order. We should be familiar with the blue order in the blue script, that this -3 of this exponent is a superscript. But again, we might need to get used to this being a subscript there. Okay, so here's switch to logarithmic form. 10 to the 0 power is equal to 1. Anything other than 0 to the 0 power is 1. In log form, it looks like this. Now, you may notice immediately that we're missing the base this time. This is called a common logarithm. When no subscript is present, it's understood to be 10. So that's something maybe a little different about logs. So when you read log of 1, it is asking for the exponent necessary to raise 10 by to make 1. Okay, a fourth example, evaluate without a calculator. So here's one where, again, we have to think about what log means. Log means what's the exponent necessary to raise 3 by to make 81. Pause if you need to. That would be 4. 3 to the 4th power is equal to 81. Fifth example, evaluate without a calculator. This one's a little more difficult. You have to know your exponent rules a little here. Log base 2 of 1/8 means 2 raised to what power is 1/8? Well, we know that 2 to the 3rd power is 8. And if you put it in this fraction form with 1 on top, you need a negative exponent. The answer is -3. 2 to the -3 is equal to 1/8. But again, the emphasis is on when it says log, it's looking for an exponent. A logarithm is an exponent necessary to raise one number to make another. Okay, sixth example, this is more difficult still. And you have to be pretty good with your exponent rules to understand this one. Log base 8 of 4. This gets into taking roots. The third root of 8 is 2, and then 2 squared is 4. So the answer here is 2/3. If you haven't brushed up lately on exponent rules, you may not know this one. And we won't go down that rabbit hole here with the exponent rules. But again, know the primary focus of this video, 8 to this power equals that. Okay, exponential template. The standard here, these standards sort of intertwine some ideas. So we're going to go ahead and throw the idea of exponential models in here. And it looks like this. Exponential, remember, is where you have a variable in the exponent and you have a proper base. So what we have in this situation is an initial value of some sort where you start, and R is going to be a rate of change. This 1 represents the 100% of the A that you start with. Okay, so if R is 0, then you're just going to keep multiplying by 1 and nothing's going to change. But as soon as you make R be something, either added to or subtracted from the 1, then the value A is going to change. If you're adding the R, A will go up. If you're subtracting the R, A will go down. T is some unit of time. Okay, so example with that, a town has a population of 5,000 and grows at a rate of 6% per year. So here's your format again. Filling in the blanks, the initial amount is 5,000. I cannot do add and subtract. I must choose. Here I choose to add specifically 6%. Remember, 6% is 0.06. The percent symbol literally means divide by 100. And then for the model, I'm going to leave it t for a moment until we want to know about what t is. Okay, I can add that. So this is the model. And by looking at this blue model, we should know that this has something starting at 5,000 and then a growth of 6%. You can see that in numbers. But remember, if you're multiplying by a number larger than 1, this 5,000 will grow. Okay, so this is the model. I can now use this model. How many people will there be in 5 years? I simply insert a 5 into the t position, and it should be something larger than 5,000. In fact, it's 6,691. Stay with this idea for a moment. When will the town reach 10,000 residents? Okay, so what we have to do here is put 10,000 in that y position, and then we're looking for an exponent. So this is where logarithms are useful, when you're looking for exponents. Now, we're not going to solve this quite yet with logarithms. The idea of this video is to understand the need for them. So in this case, I could divide by 5,000, but at this point, I have to know how to solve what we call an exponential equation, and that does require the use of logarithms. Now, you could, in this particular example, use a table. I pull one from Desmos. You can pull one from any calculator. And you can see from this table, when will the town reach 10,000 residents? Well, it looks like that 12th year it will, somewhere just shy of that 12th year. But logarithms could pinpoint that precisely. Okay, 8th example, truck worth $40,000 depreciates at 8.7% per year. Again, looking at your exponential model, 40,000 is where you start. This time depreciates means loses value. So you're losing 8.7%. That's 0.087. Again, that calculation can be made. This is the model that we can work with. We should look at this and tell that we start with 40,000 and we're losing value. We're actually losing almost 9% value. How much will it be worth in 6 years? That's simple. Put a 6 in the t position and calculate. Okay, so it's lost value down to $23,000. But if you're looking for a question that says, when will the truck be worth less than $10,000? Here again, you need a logarithm because we're looking for an exponent. Okay, I can divide by that 40,000 get 0.25, but here I'm stuck. I certainly can't divide by 0.913. That's not going to help me. I must do something to get this exponent down, and I need a logarithm to do that. And that video is coming, but again, you can use this table if you'd like, and you can see from this table that somewhere between 15 and 16 years, it dropped in value down to 10,000. The standard says this. Actually, I have a 9th example before the standard. The amount of views for a viral video is doubling every hour. So this is not a percentage. This says doubling. So in this case, you wouldn't use that same format. You could just go straight. Here's the format, but you go straight to a 2 in this position. Doubling is like a 100% increase. But when you hear double or triple or half, if it tells you specifically, then you can ignore the formula. Have the same format. You're starting at 180, you have your t, but this would go straight to 2. Now your standard, use the definition of a logarithm, logarithmic properties, and the inverse relationship between exponential and logarithmic functions to solve problems in context. Certainly this video didn't talk about every logarithmic property that there is, but it did show you some cases where logs are useful.